polynomial theorems that's going to make life a little bit easier. So the first one's the remainder theorem. And what happens is, when you divide by a linear factor, so x minus a, the remainder always turns out to be what you get when you substitute a into the polynomial. Now, if we're interested in the remainder, that's going to save us a lot of time because we don't have to bother about the polynomial division. We can sub straight in and get the answer. So here's a proof of that. There's our division algorithm, divisor times quotient plus remainder. Now, we're going to say our divisor is x minus a. So let's substitute that in. So there's our polynomial now. X minus a times the quotient plus the remainder. So what is polynomial a? Well, when we substitute a in, x minus a becomes a minus a, which is, of course, 0. So all we're left with is remainder a. But the thing is, remainder a must be the same as remainder x, because we're dividing by a linear factor, which is of order 1. Therefore, the remainder has to be of order less than that. Only possibility then is it's order 0. In other words, a constant. So remainder, when we substitute in a, is going to be a constant number. So it's going to be the same when we substitute anything. It's our remainder. So there's our proof that it turns out to be the remainder each time. So remainder x turns out to be polynomial a. Well, let's find the remainder. This is the same question we did yesterday by long division. So let's just go show that, yeah, indeed, it does actually work. Polynomial, there it is. Polynomial 2, substitute in 2, and surprise, surprise, that is negative 19, which is indeed the same answer we got yesterday using our long division. If we extend this idea one little bit, we get something very useful, and that's the factor theorem. You see, if x minus a is a factor, then what's the remainder? The remainder will be 0 because it's a factor. So if we extend that remainder theorem idea, we're now saying, essentially we're saying the remainder is equal to 0. So polynomial a is equal to 0. And that's how we can identify factors quickly. So we're going to show that x minus 2 is a factor of this polynomial, hence go and factorise the polynomial. Well, polynomial 2 sub in and we get, yes, it turns out to be 0. So therefore x minus 2 is a factor. Now it then says hence factorise. Well, I suppose we could now go and do division to find the other factor. So x into x cubed, well that goes x squared, multiply out. So far the remainder is 2x squared, but the order is greater. So the order there's 2, divisor's order is 1, so we can do it again. X into 2x squared goes 2x. That leaves me with a remainder of minus 15x. But we can keep going, they're now both of order 1. So x into minus 15x is minus 15. We end up with a remainder 0. So you might be thinking, well, what was the point of doing the first bit? Because I had to do long division anyway. And when I did long division, I still proved that there was no remainder, so it was a factor. That's if you use long division to come up with the other factor. Well, let's just finish it before I show you an alternative way. X minus 2, x squared plus 2x minus 15, multiplies together to give negative 15, adds together to give 2. I think that one works. 5 and 3 sounds good. So there it is. X plus 5, x minus 3. Now, how I would do it in reality, I would not use long division, to be honest. So we've used our factor theorem. We've found out x minus 2 is a factor. There is another factor there that I don't know. Logic will work it out. Because we know the leading term times the leading term will give the leading term. So x times something will give me x cubed. Well, x times what gives me x cubed? That's x squared. Same thing happens with the constant. The constant times the constant will give me the constant number. So negative 2 times something will give me an answer of 30. Well, negative 2 times what is 30? Negative 15. Now all I've got to work out is the x's. Let's assume that there are no x's. If I was to expand that out, how many x's would I have? Right. But we don't want negative 15, we want negative 19. So how many more do I need? I still need another minus 4x is what we're saying. Well, that must be negative 2 times the missing middle term. So negative 2 times what would give me negative 4x? That's 2x, and there's the middle term. So applying logic can sometimes be quicker than doing the long division. I mean, the long division still works. I mean, if you want to do it that way, you can do it that way. But sometimes, as I say, it can be quicker to just use a little bit of logic to rationalise it out. And so there we get our second factor. It then becomes the same as what we got before. Let's try this one then. They have given me no idea about any of the factors here. So we have to guess. We're going to try the factor theorem, we're going to have to guess. But we don't just randomly guess, we use intelligent guesses. Because we know that it must go into the constant number of 36. So I could try 1, 2, 3, 4, 6, 9, 12, 18, or 36. Hang on. But they could be negative numbers as well. So I could also have -1, -2, -3. Oh, but hang on. It's not monic. So it might be a fractional factor. Fractional factors will always be will always look like this. Factors of the constant over factors of the leading coefficient. That's why when it's monic, it's nice and easy because the leading coefficient's 1. So you're just going into that. So for this one, it's quite possible that I could have a quarter, 2 quarters, well, a half, 3 quarters, 4 quarters, well, that's 1, we've already got that one, and so on. So I could try all those, but I'll cross out the ones I've already got. So 4 on 4, that's 1, 12 on 4, that's 3, 36 on 4, that's 9. So the ones that I'm left with are other possibilities that we could try. I'll just tidy those up. But now, well, not tidy up, there's another possibility. Because, of course, 2 is a factor of 4. So now we're going to try all of those possibilities, but over 2 as well. So we could now have a half. Oh, but hang on. We've already used up 1, 4 on 2, 12 on 2, 8 on 2. So we created a new one to try, 9 on 2, and 1 on 2. Oh, hang on, 1 on 2 is the same as 2 on 4. So there's not that many new ones to try. Oh, but by the way, they could be negative as well. Look, I purposely picked numbers with lots of factors here to highlight how many possibilities you could potentially have to try. But try the easy ones. What would you try first? 1. It's an easy number to substitute in, and you keep your fingers crossed and you hope that 1 works. If it doesn't, try 2, and things like that. So, as I say, logically, the first thing to pick is 4. That's totally logical. So you pick 4. Oh, look, it turned out to be 0. That was lucky, hey? So I now know x minus 4 is a factor. Now, of course, I wouldn't have tried 4 straight away. Reality, as I say, I probably would have tried 1 straight away. 1 didn't work, so I'd go, oh, well, let's try 2. I might have skipped 3, to be honest. I might have gone straight to 4. But anyway, it doesn't matter. You work your way through it and you get there. Let's find the other factor using logic. So leading term times leading term will give me the leading term. X times what will give me 4x cubed? 4x squared, thank you. So we know it's going to start with 4x squared. Let's work out the constant. Negative 4 times what will give me 36? Negative 9. Now, x's. Well, if I was to assume there are no x's, and I was to expand that out, how many x's would we have? Negative 9x. Well, what do we want? Negative 9x. Brilliant, it's done. There mustn't be a middle term. And if you feel unsure, try the x squareds. If you were to expand that out, just the x squareds now, how many x squareds would you get? And that's what we got. So it looks like there is our factorization, except we can factorize the quadratic. We got difference of 2 squares there. So in fact, had you kept going, 4 was a possibility, but the fractional ones that would have worked would have been 3 on 2 and negative 3 on 2. They would have been the other possibilities. Might have taken us a while to get to those ones. Let's have a look at an HSC one. 2004 this one appeared. So our polynomial, and they've written it as a quotient times a divisor. The divisor's been factorised for us. And then they've written the remainder in a rather strange way. They've said it's a outside of x plus 1 plus b. but that's the remainder. Okay, so a polynomial is divided by x plus 1, the remainder is negative 11. And when it's divided just by x minus 3, the remainder is 1. So what is the value of b? Divided by x plus 1. So I know that when I substitute in negative 1, I'll get the remainder, which is negative 11. Substituting that in, we end up with just b equals negative 11. Because look, the x plus 1 becomes 0. So all of that quotient part goes. And a times x plus 1, that's going to be 0 as well. So I'm just left with b. So b must be negative 11. So what is the remainder when it is divided by that x plus 1, x minus 3? Well, the other piece of information they've given me is that when it's divided by x minus 3, we get a remainder of 1. So we also now know that polynomial 3 is equal to 1. So when I substitute 3 in, we'll get 1. That'll give me 4a plus b equals 1. The first part goes away because the x minus 3 will be 0. But now the a is not going to go away because 3 plus 1 is 4. So we get 4a. 4a plus b, and that's going to give me the remainder, which is 1. But we worked out what b is. So I can substitute in negative 11 for b. We end up getting a equals 3. Haven't answered the question yet though, because it's saying what is the remainder? Well, the remainder is going to be a x plus 1 plus b. So it'll end up being 3x minus 8. So there's our remainder. 3x minus 8 for that one. So this time we're told that when we divide by x plus 2, we get a remainder of 3. Now they haven't actually said that, but they've written our polynomial in such a way that we need to be able to interpret that. So they're saying, okay, quotient times x plus 2, and then it's plus 3. So x plus 2 is the divisor, 3 is the remainder. Find the value of a. So all right, I know that when we divide by x plus 2, we get a remainder of 3. So polynomial negative 2 must be 3. So substitute that in. Ooh, minus 2 cubed, minus 2 squared. Minus 16 plus a is 3. So a turns out to be 19. Whoa, here's an old one, 1994. So this time we'll divide it by x plus 1, x minus 4. Quotient, we're just calling it the traditional qx, the remainder rx. Y is the most general form of the remainder, ax plus b. And what they're getting at there is, look at what we're dividing by. I mean, it's factorised, but it would be a quadratic. So the order of the divisor is 2. We know the order of the remainder has to be less than that. So the most it could be would be 1. It might not be, it might still be a constant number, but it possibly could be of order 1. And so to generalise it, we'll chuck in some constants. So we're saying the degree of the divisor is 2, therefore the degree of the remainder is 1, a linear function. So part 2, given that polynomial 4 is negative 5, show that remainder 4 is negative 5. We'll put down the algorithm. Divisor times quotient plus remainder. Now, we're going to substitute in the number 4. So polynomial 4, the 4 minus 4 will go away, and we'll end up with remainder 4. They told us polynomial 4 is negative 5. So we've got the polynomial 4 ends up being remainder 4, so remainder 4 is negative 5. Further, when our polynomial is divided by x plus 1, the remainder is 5. So we know remainder 4 is negative 5. So 4a plus b is negative 5. Polynomial negative 1 is going to be positive 5. So negative a plus b is 5. Simultaneous equations. And that'll get us a is negative 2. Sub back in, we'll get b is 3. So our remainder, ax plus b, is negative 2x plus 3. Okay. 10D, I've just pointed out there, if you want to prove that the factor is not monic, so if you've got 2x minus 1, then that's when you put in the fractional possibility. And that fractional possibility is always the constant over the coefficient of x. So in this case, 1/2 is what we'd sub in.